Hey everyone, I'd like to thanks for coming to PyData Global 2024. I'd like to welcome you all to Rodrigo's talk, Understanding Polar's Data Types, and I'll let him take over from here. Thank you so much.
Thank you, Stephen. Hi, everyone. It's a pleasure to be virtually here. And for the next 30 minutes, I'll be telling you about Polish data types. And I want to apologize in advance because I make terrible jokes. And I don't think I will bother you too much with my bad jokes, but you can never be too sure. So you should be seeing my slides now. And let's get started. And thank God I noticed I wasn't sharing my screen because I was about to get started, you wouldn't even be seeing my screens. So we're talking about polars data types, and if you're here, I assume you know what polars is, but just to be sure, we're not talking about polar bears. So the polars we're talking about is this data frame library written in Rust. Over here at the bottom it says blazingly fast. You can say you can't read that because it's too small, but it says there. And apparently you can go too fast. There's such a thing as going too fast because a user recently complained that Polish is too fast for them. Obviously, I had to remove some context from the message, but I think the gist is please go slower. All right, so that's the short intro. I'm not going to teach you how to use polars because that's not really the point. This is not a Polish tutorial. I just want to tell you about the data types themselves. And the question really is, why would you bother with this talk? And why would you bother with using the right data type? Why is it relevant? Why do you need to know what data types there are and how they work and what each one is for? Well, for one, using the right data type and using the data type that is semantically correct in a situation can make your code easier to reason and to understand, reason about and understand. So that's already a very good reason, I would say. But if that's not enough for you, you also get more memory efficient programs. You get more performance because Polish is able to work properly with your data if Polish knows exactly what it should be and what's actually looking at. And by using the right data type, you often get access to specialized functions for that data type, which in turn means your program is going to be more efficient, more performant. So these are some of the reasons why you would actually bother with this. Now, this is a piece of code that we need for all of the other code examples. If you don't run this first, none of the code examples will work. So this is the king example or the king snippet for the whole talk. And with this out of the way, let's get started with a data type that you probably know already. So the data type Boolean is essentially like Python's bool. I don't think this surprises anyone. I'll just share an interesting piece of trivia because the Boolean data type in polars is quote unquote is efficiently bitpacked. And what this means is that each Boolean value, each true or each false, only takes up 1 bit in memory. And that's more than a true or false in Python. So polars makes it more efficient, and you can prove that or you can see that with a small experiment. For example, this code snippet generates 8 times n random booleans, where n is a value you can set. And if you ask polars for the estimated size of this series S, it's going to be exactly 73 in this case. So the number of bytes of the series is going to be 1/8 of the number of booleans you have, because each boolean is a bit. So 8 booleans gives you a byte, and if you have 8 times 73 booleans, you get 73 bytes. It's basic arithmetics. And this is just a small experiment you can run to verify this. Now, there's also a data type that's pretty intuitive. And actually, most of the data types we will be talking about today, they're pretty intuitive. You have an intuitive understanding of what they do. With this talk, it's not like I'm going to it's not like I'm going to teach you every single thing about every single data type. I just want to deepen your So this intuitive understanding you already have, I want to deepen it, and I want you to really understand when each data type is relevant and useful, because then you can just go through the docs and learn more about the data type, right? I don't want to teach you every single function there is. I just want you to be aware of the 18 data types that Polars has. And this one, this data type null, it's more or less kind of Python's none type, which is the type for the value none. So Python's none is a value, the type is none type. So I kind of want to say that the data type null is like Python's none, but that would be comparing apples with oranges, and that doesn't make sense. But the none is the value, and the none type is the type. And this just represents missing data. For example, this series has 3 numbers, and instead of having a fourth one, instead of being 1, 2, 3, 4, the 3 is missing and I put a none there. So this represents a missing value. And Polars represents this with a special value null. And you can see that the none in Python is seen as a null in Polars. And what's important here to understand is that the null value, this special value, it's the value that represents missing data in any data type. So any series or any Polars column can contain null values if those pieces of data are missing. And another fun piece of trivia, you can check in a series or in a column, you can check which values are missing with the isNull method or with the isNull expression, depending on your context. And this is actually free to compute. And I said I did this free because Polars has this thing called a validity mask. So this is essentially a free operation. Now, if there's one thing I want you to take of this talk is that nothing is really free. So you might have heard of there's no free lunch theorem. So when I say it's free, I'm really just talking about the computation part, because Polars keeps track of this validity mask beforehand, and this is something that represents some memory overhead. So it's free in the terms of computing because there's no computation needed. It's not free because it takes up a bit of memory. Now, this validity mask is as efficiently bit-packed as possible. And so for this, of course, this is a tiny example, but for this example where you have 4 integers, the overhead is just 1 byte. But now I have a challenge for you. Notice that on the left, I have 4 integers. And now if I double it, and if I get 8 integers in there, the estimated size now increases from 32 bytes to 64 bytes. And the number of integers doubled. So on the right here, with the none, I have 33 bytes because I'm keeping track of the validity mask. So what's the estimated size now? What would this value be? And you can let me know afterwards what you think the result is. Now I want to talk about eight different data types, which in Python map essentially to the int type. And in case you haven't understood yet, this is the perfect time to say it. These comparisons I'm drawing in these, let's call them section slides. I'm not saying that the Polars data type at the top is exactly like the Python data type at the bottom. I'm trying to draw analogies. For these more basic data types, you already understand the data type perfectly, so that's fine. But later on, these analogies might help you understand what the data type really is. And again, it's not an equivalence, it's just an analogy. In here, what are we talking about? And what's this int x? What's this u int x? Well, you probably know that Python supports arbitrarily large integers. For example, 10 to the 100, that's a pretty big number. And then we're just doing some operation with a prime number because everyone knows that this 99 billion something, it's a prime number. Everyone knows this by heart. And this is the result. And Python doesn't even, this is just immediate. If you run this in Python, you get the answer immediately and you don't have to do anything. But most data frame libraries, I'm saying most because maybe there's one that doesn't have this issue. Most data frame libraries have limitations for their integers. So they have different integer data types with these numbers on the right. And these numbers on the right, they tell you how many bits you have available to store that integer. Obviously, a bigger number means more bits, which means you can store larger integers, but it also means it's taking up more memory. And the reason I have the Rust crab mascot over there is just to highlight the fact that in some situations, because Polars is written in Rust, some of the, I would say, some of the philosophy of Rust can show in Polars, or some side effects of the fact that Polars is written in Rust can be shown in the Polars Python API, or it can be, you can kind of see through the Rust implementation. And this is just, I find it funny to understand that some things happen as a result of the fact that this is implemented in Rust. Now, I'm not saying that you only have int 8 and 16 and 32 and 64 because it's implemented in Rust. I'm just saying that it's kind of a side effect. And the only reason I'm going through this is because if you've never worked with any data frame library, this will be new to you. And the bits available here that you're using for the integers, one of them, you're going to use it to store the sign of your integer. And so you lose one, and the other 7 or the other 15 or the other 31 or 63, those are that actually used for the value itself. In practice, this means that for these data types, you get lower and upper limits. And most of the time, well, it really depends on your application, but on average, an int32 will be big enough because 2 billion is already quite a big number. And if you go to int64, you get roughly 9 quintillion. So that's pretty huge. And so there is a limitation in the sense that there are lower and upper limits, but also it's quite a big limit. And it's not you don't usually go around and work with numbers larger than 9 quintillion. So don't worry too much about this. And the U in turn, the U stands for unsigned. And the unsigned integer just means that you don't need to worry about the sign because the number will always be 0 or greater. And so you're spending 0 bits for the sign, which means you get all of the bits for the value. So the uint, the lower limit is 0 and the upper limit is twice as large as the limit for the signed integer. So there's the signed integer, which is the int, and there's the unsigned, as in without a sign, integer. And if this is new to you, there's just one very important thing you need to be aware of, and that's called, or those two things, which are essentially the same thing, overflow and underflow. Because your integers have limits, there's a limit as to how low your integer can go or how high. If you do computations that make the numbers go either above that upper limit or below that lower limit, numbers will wrap around. And as an example, I created a series with unsigned integers, and I put the 0 there. And 0 is the lower limit. So when I do s minus 1, when I subtract 1 from the series, the result I get is actually a huge number. It's this 18 quintillion or quintillion. I don't even know how to say this. Because numbers, the 0 underflows. Is this an English word? I don't think I'm conjugating the verb correctly. But there was underflow and the 0 minus 1. Instead of getting a minus 1, which is what you would expect, you get this 18 quintillion. So you need to be aware of that. Same thing with floats, as in there's also an X there that stands for the number of bits that you're going to store. You can have float 32 or float 64, and these are very similar to Python's float. In most machines, a Python float is roughly a float 64, So there's no issue in that. And float 32 and float 64, they also suffer from the usual rounding issues. I don't think, actually, if you've never done this, you can try later. You can open your Python REPL, you type 0.1 plus 0.2, and you'll get 0.3 and then a bunch of zeros and a 4. So there's a rounding issue there. And it might look like polars doesn't suffer from this issue. So if I compute 0.1 plus 0.2 in polars, I can see the 0.3 there. But that's just because of the way that polars formats floats by default. If I change the printing precision, if I configure polars with a different printing precision, I will see the rounding error there as well. So beware of that. And another thing that's unique to floats, or to the float 32 and float 64 data types, is the NaN or NaN, or not a number value. This is a very special value, and it's not the same thing as a null. So I have a series here. I have the numbers 1, 0, and the value none, and I'm dividing that by 0. And the result I get is what you see on the right. I get infinity for 1 divided by 0. I get none for... now this is difficult to say. So I get NaN when I divide 0 by 0, and I get a null when I divided none by 0. And so we can see that missing data, if the none represents missing data, the result is still missing data, because I can't divide something that's missing by 0. So I get the null. But when maths doesn't math, when I divide 0 by 0, I get not a number. This is not a missing value. It's just a representation of an undeterminate computation in mathematics. All right, so it's a very special value, but it's not the same thing as a missing value. Missing value is null, and this NaN is a special float value. Now the data type string, this is actually pretty similar to Python's str. There aren't a lot of differences. I mean, you obviously work with them in a different way, but the string is a string. It's a piece of text or a sequence of characters. And in polars, you actually have dozens of functions to work with strings. You just need to use the .str or .str namespace to access them. So there's a bunch of, maybe close to 100. I should have counted them. So next time I'll know the exact number. But there's a bunch of them, and they allow you to work with strings efficiently. So it's not a hassle to work with strings in polars. And just a word of advice, or caution, word of caution. Sometimes you'll get a string when you're reading data from somewhere, but you don't actually want a string. Maybe you want a temporal data type, or maybe you want a categorical data type. And so there's functions to convert strings to more specialized data types. And speaking of more specialized data types and the temporal data types, there's 4 data types that you understand quite intuitively already, and those are related to time. So there's something that's a date, and a date is very much like Python's datetime.date, and it's the data type that you use to represent a calendar date. So something that has a year, a month, and a day. You can get these by parsing them from strings, like I was saying, or you can create them directly if you use Python's datetime.date. So those get converted directly. For example, in here you can see the date of the first appearance of Superman in a comic book in a Python datetime.date object. And when you create a data frame around this, you get the date in polars. So polars knows how to work with datetime dot something objects. And I just said the dot something because there's date, but there's also time. So the data type time is essentially like Python's datetime.time. It's the same thing, well, not the same thing, but it's the same idea. You can create them directly from datetime.time objects. You need an hour, a minute, or the units you need are hours. Gosh, my English isn't working, sorry. You need hours, minutes, and seconds, and sometimes you can even get fractions of a second, and those can be created directly. And when you need to combine dates and times together, you get the datetime data type. I think you saw this coming, I guess. And this is again like datetime.datetime. And the main difference here is, well, besides having more units, so now we're working with years, months, days, hours, minutes, seconds, and fractions of a second. This is also what you need to use if you want to work with time zones. I know everyone loves time zones. Working with time zones is always everyone's favorite ordeal. And in this example, I have a date time with 3 different time zones. Well, you couldn't guess, but this is in my time zone, which is UTC plus 0. What am I saying? Yeah, I don't think I'm lying to you. But these 3 date times, they have 3 different time zones. And what I want to show you is that when you create a series with these date times, so I'm creating a series at the bottom, Polars will convert everything to a single time zone. So it was the same date time, but in a single time zone now. And if you use the appropriate function or the appropriate method to convert to a different time zone, you actually see that this single time zone is part of the data type. And so that's why Polar's series or Polar's data frame columns in a data frame, if they have date times, they can only have a single time zone because it's part of the data type. And this other thing next to the time zone, that's the time unit. So it's the smallest fraction of a second that defines the precision for your date time. And there's 3 time units. And honestly, I included this table. It's not for you, it's for me because I keep forgetting. And so I thought that having this here would be helpful for me. By default, you get the microseconds, which are the international system units, or which are a unit of the international system. And you need a million microseconds to get a second. And there's also the millisecond and the nanosecond. So you can work with any of these 3 time units as the smallest units of the fraction of a second. So just a useful table to have around in case you don't know this by heart. And now, earlier on, when we were talking about strings, I said that it might happen that you have strings and you actually want temporal data types. And to get those, you have 4 specialized functions in the str namespace. And the names quite clearly map to the correct data type. And there's also str ptime, which stands for string parse time, which will convert any string to the appropriate data type depending on the format that you're trying to parse. And again, I included the Rust mascot here because the format specifiers for these, they're not the Python datetime format specifiers. They're actually the format specifiers from a Rust crate, which is essentially kind of like a Python module. And the reason I'm saying this is because if you're using a more exotic format specifier, they may not match, and so you might get an error. So there's in the documentation there's a link to the list of format specifiers that Polars actually accepts. And if you want to go in the other direction, if you have a date or a datetime and you want to convert it to a string, you can just use .dt.toString. So the .dt here showing you that there's this namespace dt with lots of functions to work with dates, times, date times, and the data type that I'm introducing next, the duration. And a duration is a duration. It's an interval of time. It's essentially like Python's datetime.time delta, and it arises naturally if you're working with different times or with different dates and you do arithmetic on those dates. As an example, I have 2 data frames here, or actually, sorry, 2 series. And on the left, I have the dates and times at which I went to bed for a couple of days. And on the right, the dates and times at which I woke up. And if I subtract one from the other, I get the duration of my sleep for those 3 days. So this is quite natural when you're working with dates or times, and if you're doing some arithmetic with them, subtracting them or adding them, you naturally get durations. Or you can use say a time plus another duration to get another time. So this just arises naturally from working with these things, from making computations with them. Now I want to go to a less obvious data type, I would say, which is the data type binary. And even though you can quite easily understand that the data type binary is like Python's bytes in the sense that it just holds binary data. And even though this data type has a specialized namespace, that's the bin namespace, Polars doesn't really give you a lot of functions to work with binary data. It just provides this data type more as a utility data type that lets you hold arbitrary binary data in your data frames. For example, files in proprietary formats or serialized data. So you can hold it, you can have it in your data frames, but you will not have lots of functions to work with it. Now, we're getting close to the end, both in terms of my presentation and the time I have. So let's see if we can. I apologize. Well, you folks know that Polars is blazingly fast, and I think I'll go through this part of the presentation blazingly fast as well. But I apologize in advance. I failed with my time management skills here. But the data type decimal, also fairly easy to understand. It's like Python's decimal.decimal, but in here I cannot have arbitrary precision. I just have more precision than with float 64. So if you have some rounding issues, you might be able to solve them with the decimal data type, but this will not solve all of your rounding issues. All right, so it's not a silver bullet, it's just an extra tool. And the reason this exists, you already know this. If you have a very small number, for example, 10 to the power of minus 16, and if you add it to 1, you get a 1 back because of rounding issues. But in Polars with the decimal data type, if you set the number of decimal places high enough to 24 here, you can actually get the results correctly. And the none here on the left, it's for you to specify how many total digits you want your number to have. I'm setting it to none to let Polars compute that by itself. So I have 24 decimal digits, and if I do this computation, I do not lose the tiny number over there. So you can see it there. But again, you can clearly see that the zeros also go only up to a certain point. So it's fixed precision. It's not infinite precision. Now, I really like this data type, the data type enum and a similar data type that I'm showing you right after, which is for categorical data. If you have a for categorical variables. And this is like Python's stir enum. And the way you use an enum when you're working with categorical data is you start by defining the valid values. So you need to have a predefined set of valid values for your variable, for your data frame column. You create an enum variant with those values. So you're creating a variant of the data type, and then you can use that variant. And one good thing about this, you might feel like it's cumbersome to have to specify the number of the valid values you have. But the reason you do it is because if you specify invalid values, you get an error. So there's some I saw someone popping up on the stage, and I lost it. But there's I can do this runtime checking. Sorry, that's not what I wanted to say, but it's what you get. It raises an error.
You're good. You're good. I just wanted to recognize that it is about 30 seconds before the end if you want to just wrap up.
I want to wrap up. It's a bit ridiculous because on my end, because the best parts was not covered, but thankfully you can read it online. There's a blog article. If you scan the QR code, it will show you a link to the blog article that acted as a reference for this talk. I apologize for going way over my time.
You didn't go way over. You're right on time. You did not go way over. You're good.
Thank you for stepping in, though. I appreciate it.
Yeah, of course. Thank you so much for speaking and taking time today to be with us. Anybody that wants to continue the conversation or have questions, please feel free to reach out to Rodrigo on Discord or within the AirMeet chat. And I'm sure he would be happy to continue the conversation. Thank you, everybody, for attending. And thank you so much for speaking today at PyData Global.
Thank you very much.